This is part 2 of mechanical properties of materials. The topics that we are going to cover in different parts of mechanical properties of materials, part 1, part 2, and so on, they're listed here, the 6 major topics that we are going to concentrate. Today we are going to talk more about categories of stress-strain relationship, and we take it from there. There are different categories of stress-strain relationship. Remember that because we're dealing with a curve and we're dealing with a curve that is not always a straight line in different regions. Of course, it's part of the curve was a straight line, part of it wasn't. So we need to divide the behavior of the material into different regions. So that's why we have these categories of stress-strain relationship. And this category that's shown here is called perfectly elastic category. In perfect elastic category, the behavior is mainly defined by modulus of elasticity, or remember from previous lectures that we defined that already. It's based on Hooke's law, and E is nothing but the slope of the stress-strain diagram in the elastic region. In this region, we're not going to have a fracture. Instead, we're going to have fractures rather than yielding to plastic flow. So it's very important to realize here. If we have any kind of a fracture here, it is for the brittle material, including ceramics, many cast irons, and polymers, and they fall in that category. For steel, we are not going to have any kind of a fracture at this region unless it is extremely subjected to low temperature. So this perfectly plastic category is very important for ceramics, many cast irons, and again thermosetting polymers. And the other category is elastic, perfectly plastic, or what is commonly known to engineers as elastic, perfectly plastic. In this category, as you can see, the entire plastic region is shown by a straight line. The assumption is that we can define the stiffness by E, and once the stress reaches Y, which is not shown here, but Y is actually this line here. This is Y. It deforms plastically at the same stress level. That really help us to design the material in such a way that we have a much higher factor of safety, assuming that the material we're going to use yield point to pretty much perform our design. Again, we're going to show some examples later. So metals behave like this when they're heated to sufficiently high temperature above recrystallization. The other category of stress-strain relationship is called elastic and strain hardening. This is also another model that's used for designing, pretty much to describe the behavior, the stress-strain relationship of the material. Elastic and strain hardening. These are pretty much crude modeling of the real behavior of the stress-strain relationship. Again, Hooke's law applies in elastic region. We are going to still have a yield point, which is here. This is Y. And most ductile metals behave this way when cold worked. Let me also talk to you about another test that would give us more information about the mechanical properties of the material, and that is compression test. Again, the original area of the specimen is shown. It is labeled as A sub 0. After the compressive forces they apply to it, of course, the area would increase, and that is shown as capital A. When we apply a load that squeezes the two ends of the specimen between two plates, you can see it's going to look something like that. What we're interested here in this test is we want to make sure that we're not going to have any buckling before the material reaches its full strength. So as you can see, we may have a material in which it would perform well during the tensile test, but when we apply a compressive force to it, it may buckle before it reaches its ultimate strength. So that's very important for us to study for any material. The compression test setup is shown as such. Again, the moving crosshead now would actually move downward instead of putting the material in tension like the previous one. In the previous one, it also moved downward, but it didn't cause any kind of compressive forces. So the way we define engineering stress and compression is the same way. The only difference here is the negative sign that we put in front of the equation. A sub 0 is the original area of the specimen. The strain in compression is pretty much defined the same way. Instead of L, in this case, we use H. And this is a stress-strain curve in compression. As you can see, it is somewhat different than the stress-strain curve in tension. In this case, the plastic region is different in shape because of the cross-sectional increases as we apply the compressive load. And of course, the calculated value of engineering stress in this case is higher. So let's compare the two tensile tests versus compression tests. There would be differences between the two. However, the stress-strain relationships are nearly identical. Since tensile test results are more common, we use the tensile test result. However, we always check to make sure the material will not buckle before its ultimate load capacity, before it reaches its ultimate load carrying capacity. When we're using tensile K and N data for compression, we ignore necking. Again, this phenomenon is peculiar to strain induced by tensile stresses. So how do we test brittle material? If we can test the ductile material using the tensile testing, how can we test brittle material? The hard brittle materials, an example, ceramics, they possess elastic ductility, but they have little or no plasticity. So they yield up to a point beyond which they pretty much fracture or they break. So conventional tensile tests cannot be easily applied to brittle material. So how can we measure the mechanical properties of brittle material? We use a test called a bending test or flexure test. So in that case, the specimen of a rectangular cross-section is positioned between two supports and a load is applied at its center. Here's an example of a bending test setup and the way it actually carries out. bending of a rectangular cross-section results in two types of stresses, both the tensile and compressive stresses. On part 1 down here, this is the initial loading of the bending test, and on part 2, we actually increase that, and we highly stress and strain the specimen at the same time. Remember, by taking the material through the bending test, we can simultaneously have high compressive stresses and strain on top, the top extreme fiber of the material, and the bottom extreme fiber of the material is going to be applied to tensile stresses and strains at the same time. So it's very important to realize the bending test. It would be very useful in those cases. So brittle materials, they will not flex, and they deform elastically until they fracture, as I just mentioned that to you. So failure occurs as a result of two things here. It can occur because tensile strength of outer fibers of specimen are exceeded, or the other failure type is what we call cleavage, and that is common with ceramics and metals at low temperature, in which separation rather than slip occurs along certain planes. We call it crystallographic planes. Again, if you're interested, you need to read more on this on your text. The failure type of cleavage is a very important failure type of brittle materials. So how can we calculate the shear properties of the material? We take a cross-sectional area of the material A, is shown in this case under label part under A, and then we apply tensile stresses or tensile forces to this material. It's going to cause both the shear stress and shear strain as it is shown here in part B. When we apply the shear forces, the material has a tendency to dislocate, and the deformation of the material is measured from one end. It's called, it's shown by delta here, the small cap Greek alphabet delta, and of course the width of the material is also measured. Let's take a closer look at shear stress and strain and how we can measure some of the properties. Shear stress is defined as the force, the shear force divided by area. This is very important not to be confused by the tensile force. This is the shear force. We are talking about shear stress and strain, and A would be the area over which the deflection occurs. Very different than the cross-sectional area. And the shear stress is also, shear strain is also defined here, and that is the deflection delta by the distance over which the deflection occurs. So that's another important, two important definitions that we just defined here. We also can have a torsion test. I'm going to quickly go over a torsion stress strain curve here, because we are going to use two important parameters here. One is in the elastic region, we define the relationship between shear elastic stress strain, and that is capital G here. It's shown as shear modulus, and other terms we just previously defined here. The shear stress is tau and shear strain. So shear stress and shear strain, whereas in tensile test is related by modulus of elasticity in a shear test, and we replace that stress by tau, and we replace the strain on the right hand side, and we introduce a very important parameter here, capital G. It's called shear modulus, or shear modulus of elasticity. For most materials, capital G is roughly about 0.4 E modulus of elasticity. So the material, if we look at G and E relationship here, it shows that the shear modulus is only about 40% of elastic modulus. Again, this is an approximate number. So if we know the modulus of elasticity of a material in the elastic region, we can approximately estimate the shear modulus as 40% of elastic modulus. That brings me to the end of part 2 of mechanical properties of materials.